Good day, folks. I recently came across a YouTube clip which dealt with the linear buckling of a wind turbine, and I got interested in that problem for the reason that I'm going to mention in a minute. First of all, it is based on this article which was published a few years ago, maybe 2, 3 years ago, and it was picked up by the YouTuber below, Dr. Wagner. And he basically solved this problem using a free software, which is called Prepo Max. Okay. Now, let me show you what I did after that. I have a playlist which is for doing FEA on Catia. It's right here, and this video that I'm preparing now is going to go into this playlist. But I looked at that problem and I found it interesting, so I wanted to replicate what was done by Wagner, but using the 3D Experience software. Now, remember, the FEA solver in 3D Experience is actually the Abacus program, which is pretty much what the people in that paper used. But the Abacus interface is completely different from what you see in the 3D Experience. This is why I was interested to replicate this problem in 3D Experience. Now, I'm going to do the same thing, but in the Catia program, Catia V5, Catia V5 program. So in the presentation, Dr. Wagner mentions that the geometry of the tower and the flange can actually be taken off his website, which is right here. But in the 3D Experience example that I did, video tutorial that I did, I actually did not use these STPs, but I actually constructed that tower and the flange from scratch. It's a very simple problem, but I think it was worth doing it. Now, here, actually, you can see the tower and the flange up there. This is the wind turbine tower, and this top piece, which is actually the what is called the flange section. But if you there is also a little piece down here, a very narrow piece down here of the same thickness of 17 millimeter, which I don't use. So I have two choices. Either when it comes to doing it in Catia, I don't mesh it, which means that it's not going to participate in the calculation, or when I read the STPs into the Catia, I can actually cut that bottom piece, and that's what I'm going to do. Okay. The properties are given here, steel and its linear buckling. We're going to be doing this is coming from Wagner's website, and these are the thicknesses of these levels or stages, and the top is top flange is 15 millimeter, and in that paper, there are two load cases that's being considered. I only do the second load case. And by the way, this is from Wagner's presentation, and this is from the actual paper. And the load case that I'm going to be looking at for buckling purposes, there's a shear force here in that direction. There's a vertical force downward, and there's the weight of the object. Now you can view this thing weight of the object, but then this is the turbine that goes all the way on the top blades and everything. So that V is adding to the weight, and then there's a torsion and a moment like that. This moment comes from the fact that actually those propellers on the top make the whole thing bend, and torsion is of course torsion. Right. So I'm going to do only this second load case. Okay. All right. So let's go ahead and do that. All right, so we have Catia V5 here. Now, I used the V5 6 release 2023 X, but even if you went back to release 20, which was, or release, I don't know, 18, 19, from 20 years ago, it still works, no problem. So here, let me take this flange STP right here. See that? This is downloaded from this website that I mentioned. I drag it into Catia. It's going to open it up. You can see that. Let me close this and fit it. There we are. This is the top flange. And do the same thing with the other fellow, the tower. Here's the tower. Now, when I take the tower and drag it in, of course, you won't put it in this file. It creates another part file and puts it in there. And there we are. Okay. And yeah, I don't need this anymore. So there we are. We have two files there. Let me tile them. Window file vertically. There is the flange and there is this. Okay. So that piece at the end of the flange that at the end of the tower that I was talking about, are these pieces, which I'm going to get rid of it in a minute. Now, I don't want to work with two files, so let me copy this, go to here's the flange, copy this, and come here and paste it into geometrical set. So notice that I have now the tower is over there, and the flange is right here, which was copied and pasted. Okay. All right. First thing I'm going to do is I will actually cut this end piece. We are in generative shape design. This is all going to be modeled with shell elements, of course. So let me create a plane, and the plane goes through. I use three points, through 3 points, and the 3 points are one point over here, another point over there. Let me turn this thing around. Third point over here. You can see that the plane has been created there. And now I'm going to split. Where is the split? Split uh, this piece with that plane. Notice that it gets rid of that. That's the part that I want to get rid of. There we are. So basically we have the flange here. We have the flange, which is over here. And then there is the tower here, except that I put that thing and got it. Now, what I'm going to do is I will join these, the split and the flange. I'll join them. So let's go ahead here, join. I'm going to use the split, and I will use the flange. This was the flange, right? Okay, and then we say okay. So we have a join which is made of the tower, and this flange is attached to it over there. Very good. Why don't we apply properties to it? Let me apply material properties to it. So here is the apply material. I'm going to use the steel, and I'm going to apply it to the joint. And I say, okay, let's go ahead and change the properties so that we get exactly what we want. I'm not sure what my units are. I'm going to change my units in a minute. Yep. So let me go change my units. So tools, tools options. Okay. So parameter measure units. For length, I make millimeter, no problem. For density is kilogram meter cube, that's good. For pressure, I make Newton per meter squared, Pascal. And yeah, that's good. Okay, then let's go get the force, because eventually you have to put some force and moment on it, so might as well alphabetically sort these out, order. So force is over here. I'm going to change this thing to newtons, and moment. There is where's the moment? Let's go find the moment. moments right there, Newton meter, Newton meter, and then we say okay. Good. So now I'm going to double click on steel, select the analysis tab. So here we have 210 gigapascal. I can write it like that, 210 GPa. Okay. And then this is 0.3. And the density is 7850 coming from that paper. Kilogram, 7850 kilogram per meter squared, and these things are irrelevant. Good. So we have the proper material on it. And while I'm here, I'm going to create 2 points, one at the center of this top circle and one at the bottom, which is the center of that bottom circle. And the reason is that later on, when we apply boundary conditions, we can create a virtual part and apply it to that point instead of the edges and things like that. So let me do the first one, point, and use a center of a circle. So let's go up here. I select this. There's basically 4 circles here, but it doesn't matter. I just select one, and it creates a point right there. Okay. So I can call this thing. I can call this thing. Yeah, there's one. Let's do another one at the very bottom here. Another point at the very bottom. I select one of these arcs. It's going to create a point right there. You can see that. Very good. Okay. So that takes care of this. Now, in that paper and in Wagner's work, they use a very, eight noded shell element, but I'm going to use the standard 6 noded triangular shell element. So basically free mesh. What I'm going to do is I go to analysis and simulation, generative structure analysis. Okay. In Catia, you have to do a static analysis first and then insert the buckling. So that's what I'm going to do. Static analysis first. Don't worry about that. Okay. Let me change the rendering here so that you can see things easier right there. Okay, so let me turn this thing around, by the way. All right, we have to mesh this thing because there is no solid element. It doesn't mesh it automatically. We're going to mesh this thing. And where is the element type? Here is the element type. This is shell. You can see that. Octave triangle mesher. You select this. You select the joint because remember I joined everything and I use a element size of 100 millimeter and parabolic, and that's pretty much it. We say okay. Now if you want to see your mesh, right click mesh visualization. Okay, so if you zoom in, you see it like that. I don't know. I'm going to make it bigger actually. I'm not going to use 100. I'll make 200 and see how it looks like. That was unnecessary. It was too small. Sure, I'll give it like this. No problem. All right, no problem. Deactivate this. Good. Now, notice that I haven't specified the thicknesses. So what I'm going to do is I put a nominal thickness of, notice that there are 1, 2, 3, 4, 5 levels of 15 millimeter each. So to make my job easier, I put 15 millimeter on everything, and then I come back and modify the ones that are not 15 millimeter. So let's go here. We're going to apply a 2D property, select the whole thing, and I put down thickness of 15. Everything will have 15 now. And then I can come back and change things as they are. For example, here's a property, put the cursor on it, right click down here, see that? It says local 2D property. You click on it. Okay. So notice that the very bottom four, they actually have 17 millimeter. So I select this and I select that. I turn it around. I select the other two sides. This one and that one. And this one is going to be 17. 17. Okay, good. Then the next two levels is going to have 16. So let's go ahead and do that. So once again, you put the cursor there, right click on the properties, right click local 2D property. So I select this piece, that piece, the one above it, the one above it, turn it around. And now I make this thing 16. 16. Okay, so notice that the four patches at the very bottom is 17. The next 8 patches is 16. Now I don't have to worry about these because these are 15, but at some point I have to, I have to go down to, from 15, I have to go to 14. It's easier if I start it from the top. Maybe it's easier. So the top is 50. Go here. Once again, put the cursor there. 2D property, local 2D property. I select these 4 pieces on the top. Four faces on the top. And I'm going to change that thing to 50. Oh, these things actually, I screwed up here. So let me delete this. Try it again. I think I picked something else also. 2D property. I want just this piece and just that piece and that one, and turn around just this one. Now I want these to be 50. Good. So the next two, I believe, is going to be 13. So let's go and do this. Again, insert local 2D property. Let me make this thing 13 so that I can see what I'm picking. So, what are they? There is that guy and the fellow next to it, the fellow below it, and below. And turn this thing around. It's kind of hard to do it like this and like that. I think there's 2 more patches on the side. Yeah, I think so. Yeah, I think it's this one and that one. Altogether, there is 8 faces. We say okay. So you can see what happened here. On the very top, those 4 is 50, the next 8 is 13, and finally 14. So that's going to be how many? There's 1, 2, 3, 4. Okay, 14. So let's go to another one. To the property. I'll make this thing 14 so that I can see what I'm doing. And let's start picking. Okay, these are all taken care of. I need this one. And I need that one. And this and that. And this and this. This and this. So far, there's 8 of them. I have to turn around and pick them from the other side. That's kind of hard to do. 1, 2, 3, 4. A little bit more. And what is left here is going to be 1, 2, 3, 4. And I say, okay. So what happened is that we have 50 on the very top, 8 patches of 13, and 16 patches of 14, These are 15 millimeter because that's what I did in the beginning, nominal value. And then you go to 16, 17, the last one, the very last one, remember, I actually deleted it. Okay, very good. Excellent. Now, if you don't want to see these things, you can always hide them. Hopefully, I didn't make a mistake. Now, that takes care of the mesh. That takes care of the mesh and the properties. And now we're going to create our what is called the virtual part because I want to attach this to that top edge. So the virtual part, let's find it here, somewhere there. If not, I closed it. I can reset my toolbars to get them. I don't see them here. So if you don't see them, then you go and reset everything. Let's go here. I must have deleted the toolbar here. So let's go to Tools, Options, Tools, Customize. So Toolbars, Restore All, Restore Position. It's doing it. Hope it didn't crash. Not responding. I don't like that. Unfortunately, I did not save either. Let's give it a minute. This should not happen. Good. Scared the hell out of me. Actually, it did not restore. So let me try one more time. Uh, you know what? Since that one crashed on me, let me go ahead and see whether I can find it myself. View, toolbars, virtual parts. Do we have any virtual parts here? Yeah, virtual part. Wow. Okay, so let me do a rigid virtual part. I select for support one, I select that point that I created on the top. See that? This point. If I'm having a problem picking it, let's do it like that. Okay, so sorry, what I need to do, I can't select the point, that's handle point. I select the edges, 1, 2, 3, 4, and for the point, for the handler point, by default, it's going to be that center point. But if you don't want it, you want to actually create a handler point somewhere else, which I don't. This is fine. I really didn't even need that point, but that's okay. So I select this point. This is going to be the handler point. This is the top, and I do another virtual part at the very bottom. Another rigid virtual part at the very bottom. The edges. And by default, the handler point is going to be at the location that I created the point at. That's the centroid of basically what I picked. So you can leave it like that, or you can, for the handler point, you can select that point, no problem. All right, good. Now, what we're going to do is we're going to clamp that virtual part at the very bottom. So here's the clamp. You select the virtual part. You can either select it from the screen or from, let me see. So let me, so I can select it from the streams or from here, of course. Is that the bottom one? Yeah, that is the bottom. Good. And that's clamped. Then I apply loads on the top. And let me show you what happens here. If you go to force, let me go here, distributed force. Now, remember, I want, oh, first of all, let's do gravity. Gravity, here's a gravity. This is it. Acceleration, downward acceleration, 0. Oh, not downward, hang in there. This is in the y direction, right? Because of the way things are in y direction, and I put down minus 9.81, or should be meter underscore S2. I forgot to change the unit of gravity, so it was inch per second squared. Now I type minus 9.81 meter per second squared in the y direction for the whole thing. And notice that that's the correct direction. That's okay, no problem. Now, for the force on the top, I can remember what I have here is this configuration. So we want 4 meganewton down meaning the direction y in this case, and Q 1.6 meganewton in that direction. So I can do these things separately, or I can do that in the same for both of them in the same dialog box. I like to do it separately because it shows me the direction by itself. So for example, let me see now. This is in the y direction. So let me get rid of that. Minus 4 meganewton, right? So 4, 1, 2, 3, 4, 5, 6 on that virtual part. Notice that the direction is shown to me. If I put another direction here, then this tells I don't know what I've done. Okay, so we say, just realize that there is a clamp here. Is there a clamp there? I'm not sure. Let me see. I count the bottom piece, didn't I? Oh, I put on the wrong thing. That clamp, that's wrong. That should not go on the virtual part. Let me, oh, 2. That's okay. Yeah, the bottom should be clamped right there, not the top one. Okay, good. Now we do another force in the direction, now what's this direction? This is direction Z, right? So, cancel that. We already did the force, right? Yep. So another one in the direction on the virtual part, but not direction Y, but direction Z minus 1.660 e to the 6. So that's minus 1.6 meganewton right there, this way. Okay? And then we say, okay. Now we also want a torsion, 22 in the direction Y. So torsion is under not distributed force, it's distributed moment. Okay, so that'll be direction Y. We get rid of these. Direction Y, 22, 1, 2, 3, 4, 5, 6. Visual part. That's this. This is that fellow. And then, what is that? For moment 30 meganewton. So make sure that the direction is correct though. So let me apply another moment on that same virtual part. Get rid of this. so that I can see what I'm doing. It's about the x-axis, but probably minus. We're gonna have to check the direction of the uh, thing. Minus 30. 1, 2, 3, 4, 5, 6. Let's check it out. Oh, not there. In direction x. That's 0. Minus 30. 1, 2, 3, 4, 5, 6. We say okay, and I think that agrees with, yeah, that direction seems to agree with the drawing here. Yep. Okay, good, good. So let's go to back there. Let me save everything. File, save management, analysis, save as, November. Yeah, that's good. That's okay. Because it says there was an STP file, etc., etc. Now, if I solve this, remember, this is a static case. But in Catia, if you want to do buckling, first you have to do static. So linear static, so everything is linear. Compute. Let's go ahead and see what happens. Nothing fancy, it's going to bend. Done. Okay, so let's look at the deflection. Yep. Let me change the rendering here. I don't want to see my elements. Show me the elements. There we go. And I mean, obviously, if you want to do, you can do animation. This is going to bend the way it is. Okay, fine. But that's not the 257 millimeter, by the way. Now, we're going to do insert buckling case. When you do that, it says, okay, where is your static analysis that you did? What I did is right there. So I have to select this, and then you say, okay. Now, if you look, there's a buckling case has been inserted. If you double click on this, double click on the buckling case, it says that 10 modes are going to be extracted, buckling modes are going to be extracted, and it's going to do that many iterations for each extraction. If it says there's too many, it diverged because, or there was an error because there was not enough number of iterations, we come back and change this thing to something bigger. Okay, let's leave it the way it is. Let's leave it the way it is right now and run it, and we may have to come back and adjust that. So let's do everything. Because I said everything is going to do static again, and it's going to do buckling next. But it may come up with the conclusion that 50 iteration was not good enough. Go and increase it. We'll see. Looked it worked. So okay, so let's look at the deformation mode. There we are. If you double click on this thing, this is for buckling, and if you click on the occurrences, these are the buckling factor. The first one is 1.4, and if you look at the paper, oops, let me bring up the paper. Let me bring up the paper. Okay, I brought up the paper here, which agrees, by the way, with what Wagner is doing. But if you scroll down, there it is. This is load case 2. First buckling mode, 1.401. Second buckling mode, 1.559. So if you go back here, first buckling mode, 1.40. Second buckling mode is, it's probably this one, 1.5, yeah? 1.495. So basically we have recovered these two. Wagner's calculation with that free software is also very close to this. Now, If you want to look at, by the way, the buckling mode, if you look at it here, second buckling mode looks like that. First buckling mode looks like this. Okay, so let's go ahead and check it out. We can see it from here. So let's plot the displacement. Okay, so double click that, double click, average ISO. There we are. So what you see there, this is the second mode. Make sure that it is correct. Occurrence, yeah, that's the first one, first mode. So that is comparable with what the fellow is getting there. And if you modify the loading so that this is what you got, you're going to get very close to these values. This is without the torsion. As a matter of fact, let me go ahead and do that. So let me go ahead here. Let me go ahead to distributed force here, and that one I believe is okay. I'll change that. This one should be 1.76, I believe. 1.76, you can see 1.76, and there is no torsion. If you go back here, there's no torsion. Oh yeah, there is a moment, but there's no torsion. 33. So let's go to the moment, this moment. That should be 3.3 or 3.3, which is 33 meganewton. And this one is going to go. This one is going to go. All right, now let's go ahead and run it. I hope it's not crashing on me. Yeah, see that number of iterations insufficient, so it's okay. Let's go back to that buckling. It was here, right? Double click. Let's change that thing to 100. See what happens. And then we're going to run it. I've done it, so I know it's going to work. It's just that I don't remember whether I put 100 or 150. So if it doesn't finish with 100, I'll just give up. You can try 150. Well, I'm pretty sure it came very close to those buckling loads that you saw in the paper. I think it's going to be around 3, something like that. First buckling load is going to be around 3. Just give it a minute. have this vibe uh, saying that it's going to ask for a larger number. We'll see. No, it did work. Okay, so let's go and look at the translation. Activate this. There we are. Oh, look, by the way. Where does it occur? Down here. And where was it supposed to happen? Down here. What about the value? Should be first one is 2.9, 2.9-ish. So let's go and double click on this. There you are, 2.9. And these are the other modes. Great. I think it was worth a try. All right, folks, good luck.